We're going to start off with Jean-Phillipe. Jean-Philippe's got a background in chemistry. He's worked for Chemotech for several years, since 2013, both in the business and technical side of the business throughout the world areas in Asia and the Middle East. Currently, he's the general manager. His hobbies are horse riding, and today we're going to start out with him. So help me welcome Jean-Phillipe.
Thank you very much for the introduction. So good morning, everybody, and thanks for ATC to let me this opportunity to make my presentation today. So today I will present one of the latest systems we have developed for online measurement of crude oil by online GC-MS. So first I will introduce a little bit about the crude oil, which most of you know well, and present the solutions in a different step, the composition of our systems, different modules, and then I will go over the analytical results we obtain by testing repeatability, identification, memory effect, and a conclusion on the system. So crude oil is a complex sample. It's a liquid complex sample made of a big variety of alkanes, cyclic alkanes, alkene, aromatic hydrocarbons. So more than thousands of different hydrocarbons containing up to 20 carbon atoms together. So that makes a challenge, analytical challenge to measure such a complex mixture. Oil platforms are often remote, not close to any lab for measuring. So there is some need to measure this on the field, because sample collection on field followed by laboratory analysis is time consuming, and there is a risk of sample deterioration for some reactive molecules which can react together during the time of transportation or with temperature effect, etc. So in Chromatotech, we have developed solutions for this requirement with online auto GC-MS and FID, coupled with a liquid sampling module, because here we need to collect the sample under liquid phase, and to deploy easily on the field, we integrate also a gas generator for standalone solutions, so no need of any cylinder, and in a transportable cabinet. So this is what looks like the system, which is more or less 1.2 meter high, and it's a compact cabinet on a wheel, so it can be deployed on the field and connected to a fast loop of liquid oil. So it combines H2 generator and zero air generator on the lower part of the cabinet, and then a rack-mounted auto GC-MS system, and on the top side a liquid sample module. So the system is made for online liquid sampling, which can be directly connected to a liquid fast loop. So the fast loop is connected to the pipeline of where we need to connect to collect the crude oil. So we need to have a pre-filter system before the GC-MS. Again, it's a transportable cabinet. So here is a small introduction about the liquid sampling module, which is controlled by software and electronics. So it allows to collect the samples and to make a multiplexing system. So we can have up to 7 different fast loops of crude oil connected to the same unit. And the system is able to collect automatically one or the other by a method or a sequence. And we also have other channel, let's say, where we have rinsing solvents for automatic cleaning of the liquid sampling module. But also we connect one vial with a liquid standard, which can be automatically selected by the system to control the performance from a liquid mixture of alkanes or any liquid standard of interest, and one vial for the waste when we are doing rinsing. So what we can see is on the picture, which is a bit small, but the sample, in fact, is collected by an electronic syringe allowing to collect a sample without any pressure. So we can connect any sample collected manually or a sample from a fast loop, which is flushing continuously the fast loop, and the system will collect only on demand. So that's convenient because we can switch between the fast loop of the process directly connected to the GC-MS, but also a rinsing solvent, a liquid standard in a bottle, or any manually collected sample in other location. So yes, as mentioned, the sample is collected electronically by an electronic syringe, so which is sucking the sample through the system. So the system is composed by two valves, one multi-position valve, which is allowing to select, the different sample, fast loop, solvent, liquid standard, and when we select a sample, then the syringe sucks the sample through this multi-position valve and up to a valve with an internal loop of 0.1 microliter. So then the sample is already in the internal loop, and after that we can inject this internal loop into the injector of the GC-MS. The system is automatically making a backflush of the filters with rinsing solvent after each sample. So this allows to make automatically cleaning of the system to avoid contamination, clogging effect, or memory effect when we switch from different samples. So then here we go to the GC-MS. So we inject into a heated injector with a split to vaporize the crude oil. So the 0.1 microliter crude oil injected automatically and directly into the GC-MS. In this case, we was focused on the light hydrocarbons. So a backflush mode have been configured to have the C13 plus backflush in the pre-column and sent to the vent. So they have not been going to the detector. But depending on the method, we can go further. We can go up to C40, so with 40 carbons up to the detector. It depends on which area of compounds we are looking for with the system. This is after a GC-MS method. So in this case, we was looking more on C6 to C12 detail of hydrocarbons composition. So we set a temperature gradient oven of the column from 36 to 200 degrees, which is enough to separate the compounds of interest. And on this system, after the column, we have two detectors. So we have a FID detector, so flame ionization detector, for quantification. And we have a mass spectrometer detector, which we use more for identification, even if we can use both for quantification. But the advantage of the FID, it's a linear detector, there is no aging effect, and we can use a theoretical response factor for the quantification, which is a strong advantage, because in the crude oil, we have so many compounds, we cannot calibrate all compounds which can be found on the system. So that's the combination of the two detectors we use mainly. So the mass spectrometer is a quadruple with a pre-filter and electron impact for ionization. So to be able to use a NIST library with a 7 electron volts ionization. And so we have the mass spectrum compliant to the NIST library. So then we calibrate the GC-MS on a few alkanes in this case. So we use a liquid mixture of a linear hydrocarbon from C7 to C12 here, where we can see the concentration in a microgram per liter, around 5 for most of the compounds. And in order to qualify the instrument, we do 6 consecutive injections of the same liquid standard. We also do analysis of real crude oil samples, because that's the interest of the system, not only to analyze a clean and pure calibration standard, but then the real life is more difficult, and crude oil can be very different composition depending on where it comes from. So we get some different samples collected from the field, and we can see only by color and probably most of you know more the crude oil than me, but there is different viscosity and color, and the darker samples have been necessary to be diluted because of the viscosity was too high to be automatically in the system. So here, some result of the repeatability. So on the calibration mixture, we obtain a chromatogram like this. This is the FID chromatogram on the left and the MS chromatogram on the right. So they are the same, which is a good sign because they are at the end of the same column. And what we obtain is a relative standard deviation better than 5% on the peak area for the 6 consecutive analysis of the calibration mixture. So this is a quite good RSD because here it's considering the complete analytical chain, the liquid injection, vaporization, and GC, and the detection measurement on the peak area of the chromatogram. Also here is to see 12 hours repeatability on the system. So on the left, it's the signal in peak area. So without any calibration curve, we can see the repeatability over time. And on the right, it's about the retention time of the targeted compounds from the liquid standard. So we can see they are quite stable, which is very important to ensure a more accurate and good identification. Because even if you have GC and MS, there is so many compounds. So if we want to be sure, the retention time stability is quite important because, for example, the alkanes fragmentation by GCMS are more or less the same between each one. So if we have too much drift, that can make more difficult to know which alkane we are looking for. So here, an example of, so it's hard to see. You can only see some color, I believe. But it's an example of identification on a real crude oil sample. So that shows how complex is the sample. And we are looking only from C7 to C12. So it's a portion of the crude oil composition. But we have the FID chromatogram and the MS chromatogram. And on this real sample, what we find is we identify more than 50 hydrocarbons. So 50 compounds have been identified by the mass spectrometer. And even if the GCMS is a reference method for VOC's identification, as I mentioned, like the linear alkane, they have a quite similar mass fragmentation. So if we want to be sure, we need to alternate between the liquid standard injection to validate the retention time and then the real sample. And then we have 100% confidence in the identification between the liquid standard as a reference, which can be injected anytime because it's available on the system, and the GCMS identification. So response factor, again, because here MS can identify quite accurately all the compounds, so that's a very strong features on the field. But then for quantification, because FID, again, is a stable detector, it's a flame, no aging on the flame over time. Our FID have a stability for 5-10 years. We can use a theoretical response factor, which is based on the number of carbon and hydrogen bonds, and when they burn, there is an energy release which is measured. So this response factor, we have a library, and we can quantify even by calibrating each individual compounds. So that's a strong feature, because on the field you cannot have the 50 hydrocarbons you identify on this sample to calibrate. And then after this work is done, we can update easily the substance table, and automatically these compounds will be monitored and quantified every cycle. So then here, it is a repeatability on the crude oil sample. So the same crude oil sample in a vial have been analyzed consecutively 6 times. And we can see that the RSD on all compounds is better than 6%. So even with a large amount of compounds, which is making more difficult the repeatability because of the number of peaks increase, so the speciation or the chromatographic peak shape can be affected by the number of peaks. Even in this case, we have a very good repeatability on these compounds. So then, for crude oil, as it is kind of dirty or complex sample. One of the challenge is not only the analytical performance, but if we move from one sample to another, how to be sure we have no memory effect, no contamination from the previous sample. And that's part of the design of the system, is to clean every cycle the liquid injection system and the pre-colon and the colon to ensure there is no residue. So to show that, we make a crude oil sample analysis followed by 2 blanks. So no injection. That means we don't inject any more liquids, but we just make another analysis 2 times of the GC. So this is to validate the chromatography part have no memory effect. And what we observe is only 2 compounds have been identified on the first blank. So we have more than 94% loss for the 2 remaining compounds. So that's a good, we can see on the chromatogram, like the dark brown is a real sample, and then the red baseline, this is the blank just after the oil sample. We can see it more in detail. So the first blank, we have a very small peak of residue, which can be most of the time be not significant for the analysis of the real sample. And on the second blank, we have nothing. So we can confirm that the GC system have no memory effect from the sample. And in the note, we mentioned some details about how this memory tests have been done. So we didn't change the original liner, septum, and guard colon during all the measurements. So that means we don't make any service or maintenance during several weeks of analyzing these liquid standard or real samples, because the system is designed to clean as much as possible at every method to decrease the frequency of maintenance. Because in the lab, most of the time, it's easy to change the liner, the filters, or the septum, or the columns. But where you are on the field, that is more challenging or more difficult. So to conclude on this system and the brief introduction of this auto GCMS, so it's a fully autonomous solution because everything is done with only electricity power supply, because carrier gas is hydrogen from the H2 generator. Then there is zero air generator to make the FID fuel gas and all dilution gas and switching the valve, etc. So we don't need any cylinder, so that's easy to deploy on the field also, because a hydrogen cylinder is not all the time friendly. It's a big reservoir of explosive gas. It's a transportable cabinet because everything is integrated in this 1.2 meter cabinet. We have showed that there is no memory effect and repeatable result. We can identify easily new compounds with a mass spectrometer on board, and the NIST library is installed within the system. So we don't need any external computer for operation. And here we show one method, which was a target of C7 to C12, but we can adapt to different liquid samples or various field application by adapting the column, the method, and even the sampling system. So thank you very much for your attention. And I'm on the booth 319 on Chromatotech booth. If you have more questions, or if you have questions now, I will be pleased to answer.
Any questions?
Excellent paper. Just a quick question. What's the analysis time? I was trying to read the cycle time at the bottom, but my eyesight wasn't good enough.
So on this system, the cycle time was 1 hour. So every 1 hour we get a result.
Any other questions?
In the analysis of the mass spec data, that seems to be fully automated. Is there a need to have that validated by a human? Is that sometimes are there, could you shed light on that process of like how reliable that data analysis by a machine would be versus a human? Is my question making sense? Like, you know, you have the mass spec data and it's automatically translated into results into identified compounds. So is that process like very accurate, or do you find yourself having to have a human validate that regularly?
Okay, I got your question. So thanks, it's a very good question. So if I understand well, your question is, does the automatically provided data from the mass spec are accurate, or is there a need to have some data processing or data check? And in fact, the system have, so I show that there is a liquid standard, and in automatic mode, we can put in a sequence in a day, one or twice. It's on the analysis of this liquid standard, and we have a function in the software to automatically compare this data, are they good as expected or not, to validate the performance of the system on a known sample. Then automatically we can get a trust in the data, because if once a day automatically the system is checking a mixture at a known concentration and composition, and we get at better than 5% the expected value, we can trust the provided data, and the system is, we'd say, validated. After the MS is showing a list of compounds, automatically we get a list of compounds and concentration provided. So based on the system is validated, we can trust the data. But after, depending on the complexity of the sample, that's not only one way to validate the system, but every data are fully traceable and on board, so they can be controlled anytime there is a raw chromatogram and the raw result for in the computer.
Any other questions? We probably have time for one more question. Anybody? All right, let's think. Jean-Phillipe.
Yeah. Thanks again.
Next up, we have Ruth Howieson from Emerson. She's the Director of Product Management. She got her degree from the University of Manchester and her PhD from the University of Bristol. She worked for Quantum Cascade after leaving university, and that was acquired by Emerson in 2014. Her hobbies are enjoying the beautiful Scottish countryside, both walking and cycling. So, thanks.
Thank you, Sarah, for the introduction. Hello, everyone. This is my first time at ATC, so I'm very happy to be here. And I'm going to be talking to you today about optimizing gas analysis in carbon capture, utilization, and storage. So first of all, just a quick overview of what I'm going to talk about today. So I'll start by talking about carbon capture, utilization, and storage, going through the various process steps and the opportunities for gas analysis that we have within them. I'll then talk about our gas analysis capabilities, the different types of analyzers that we've got, and how they can be used in CCUS, and then I'll go through some case studies before concluding. So firstly, what is carbon capture, utilization, and storage? Well, it's a suite of technologies that can make a meaningful difference in our fight against climate change. And it features heavily in a lot of different countries' pledges to reduce their CO2 emissions. Essentially, what we do is we capture CO2 from the atmosphere, we capture CO2 from its emission source to prevent it from entering into the atmosphere, or it can be captured directly from the air. Once it's been captured, it can either be stored or utilized. To store it, it has to be purified and liquefied into a condition that's suitable for long-term storage and isolation from the atmosphere. It can be utilized either directly or indirectly following conversion to another component, and that might be at the site that it's captured or after it's been transported. So why is CCUS important? So this chart here shows the reduction in emissions from the energy sector in the Sustainable Development Scenario from the IEA. So this is showing emissions, CO2 emissions from the energy sector falling to net zero by 2070. Carbon capture is the purple part of this trace. So you can see it's making up around 15% of the cumulative reduction in emissions, and by 2070 has taken out 10 gigatons of CO2 from across the energy sector. The contribution of CCUS in this scenario is growing over time, and that's due to technology improvements, costs falling, and cheaper abatement options in other sectors being exhausted. And this is compared to the stated policy scenario, so that is the current commitments made by different companies as to their CO2 emissions, so above and beyond that. So I think it's fair to say that today adoption of carbon capture has been relatively slow globally, but in 2024 we've seen a significant growth in the CCUS facility development. So there are now 50 facilities in operation and a further 44 facilities under construction, and actually a lot of those are in the United States. So between those facilities, either in operation or under construction, they have the capability to capture over 100 million tons of CO2 each year. And to put that into some context, the natural sinks that we have for CO2 take out around 200 million tons of CO2 per annum. But currently, by burning fossil fuels, we release around 37 billion tons of CO2 into the atmosphere. So you can see it's only a fraction of what we're currently emitting through anthropogenic activities. There are also 600 projects in the pipeline, and that's reached record levels. And you can see it has the potential to be a rapidly growing market. But to meet the CO2 emissions target in the IEA Sustainable Development Scenario that I just showed, we would need over 5,000 carbon capture sites by 2070. So whilst there are clear environmental benefits to CCUS, the economic drivers come from cap and trade schemes. So here, a credit is earned when a ton of CO2 is removed from the atmosphere and spent when a ton of CO2 is emitted to the atmosphere. And the government sets emissions caps for different sectors, so things like oil and gas, energy, transportation, and emitters must stay under that cap, either by reducing their emissions or by purchasing credits to offset emissions. So there are a number of pros and cons. So overall, this does drive reductions in emissions and gives companies flexibilities on how they can comply with the different emissions limits. Cap levels typically decrease with time, which drives further reduction in emissions. But on the other hand, it can be quite complex to set the cap levels. It needs to be a level that's both achievable but gives a meaningful reduction in CO2 emissions. So that can be quite a complex process. And in fact, the cost of credits and the fines associated with penalties can be cheaper than reducing emissions in some cases. So next, to look at the CCUS value chain. So this is the post-combustion CCUS. So we start on the left-hand side with carbon-intensive processes, so things like natural gas extraction, combustion of fossil fuels. The gas that's being produced, the flue gas that's being produced, would then go into a carbon capture plant to extract out the CO2. That CO2 is then purified and liquefied before it's transported, and that can be through pipelines or by vessel. And it can then be utilized, so commonly through enhanced oil recovery processes that also gives underground storage, and then direct and indirect uses. So the most common and mature technology used to capture carbon is amine-based absorption. So in this process, the amine-based absorbent captures the CO2 from the flue gas, which is then passed through a stripper, where the solvent's regenerated and the CO2 is extracted. So this has a very high capture efficiency, but it has a high energy requirement to regenerate the solvent in the second step. The opportunities for gas analysis in this part of the process are shown by the blue bubbles. So the flue gas after the desulfurization process can be monitored. Also the vent gas after the absorber, and the resultant CO2 to monitor for any impurities. So following on from that, the CO2 is liquefied and purified. So it goes through a series of cooling and compression stages to bring it into a condition that's suitable for storage or transportation. So at this part in the process, it's important to measure impurities such as moisture, hydrogen sulfide, and methane, as their presence can cause acidic components that can lead to pipeline degradation. So monitoring of the purity of CO2 at the start of this process is essential to make sure that those components are at sufficiently low levels to maintain pipeline integrity. And finally, the CO2 can be stored underground. Here it's being sequestered for long-term underground storage, which involves injecting the captured CO2 into rock formations deep underground to permanently remove it from the atmosphere. The success of a carbon storage project relies on three main factors, so the storage capacity, containment, and injectivity. And obviously we're looking to minimize leakage to ensure the long-term success of the containment. So here, opportunities for gas analysis are at the head of the well to monitor the gas that's being injected and also to monitor for any leakage. CO2 is, of course, a useful chemical. Around 230 million tons of CO2 are used in industrial processes each year. So things like plastic production, concrete curing, and synthesis of different components such as methanol and urea, and also commonly used in the beverage industry. So next I'm going to talk about some of our gas analysis capabilities and how they can be used in CCUS. So first of all, gas chromatographs. So GCs work on the principle of separation and detection, where gas samples pass through a column which separates out the different components. They can then be detected by a particular detector type, so things like thermal conductivity detector for inert components, flame ionization detectors for trace hydrocarbons, and flame photometric detectors for trace sulfur species. The chromatogram that's obtained can then be analyzed. The peak position identifies the component, and the area quantifies the concentration of what's there, and the precise mixture of the gas can be determined. So in CCUS, the table on the left-hand side is showing some of the different components that can be measured with their detection limits and the different detector types that are used. GCs are very good at measuring complex gas mixtures and can pick up a range of different components using the different detector types. In terms of the different challenges, well, we can't measure argon and oxygen separately when both are present. We can't resolve them. The LOD for water is too high in this application. You can see it's not listed. And cycle times, as for any GC, are in the order of minutes. So we have laser analyzers, which is based on direct absorption spectroscopy. So here we're using the Beer-Lambert law to calculate the concentration. The only variable within the Beer-Lambert law is the concentrations of measurements don't drift with time, and that means we don't have to calibrate very frequently. We can use different laser types to measure gases in the mid and near infrared regions, and this is a very high resolution technique. So this gives very good immunity to cross interference, gives very selective measurements, and it can be beneficial to work at low pressure. I've shown in the chart on the right-hand side some spectra taken at different pressure, and you can see at lower pressure they sharpen up, and that can be advantageous in some applications. So in CCUS, again, a table on the left-hand side showing some of the different components that can be measured with their detection limits and the type of laser that's being used. So in terms of strength, so we've got both QCL and TDL technology. Laser analyzers offer the lowest detection limits for most components, and they give us fast and continuous measurements. Laser analysis is very good at measuring small light gases, but it can't separate out combinations of gases, so things like non-methane hydrocarbons, we would just be measuring individual components, and it's also limited to smaller molecules. Once the molecules get bigger, the spectra broaden, and they can be more difficult to analyze. And finally, process gas analyzers. So here, using a mix of traditional technologies to make a range of different gas measurements. So we have non-dispersive infrared and UV to measure a range of different components, electrochemical sensors for things like oxygen and H2S, thermal conductivity sensors for inert components, paramagnetic for oxygen, and chemiluminescence detection for NOx. And we can install multiple different technology benches into a single analyzer, which gives a very versatile and configurable gas analyzer. Each technology has its own strengths and weaknesses, and we can measure a wide variety of different gases. So again, a table showing the different components that can be measured in CCUS applications and the technologies that are being used and the detection limits. And so here we have the widest range of measurements using the different technology types that are available, and the lowest detection limit for oxygen using electrochemical. The LODs for inert components aren't as low as a GC though, and the TCD measurement's non-specific, so we have to be conscious of that when specifying an analytical solution. So next, I wanted to show, this is a summary of some of the projects we've been asked to provide solutions for over the past 2 or 3 years in CCUS applications. And I just wanted to highlight here firstly, the complexity of the analysis required and the range of different components that need to be measured in some cases, and also the fact that no two projects are the same. So whilst we see similar requests for certain molecules, the ranges can be different, and the actual gases that are required to be measured are different in each case. So there's some commonly requested components, things like CO2, nitrogen, moisture, but taking moisture as an example, you can see in one project it's a 0 to 10 ppm range and a 0 to 125 ppm range in another. And these complex requirements come from the different capture technologies that are being used, as well as the different measurement points within the CCUS value chain. So we tend not to see two applications as being the same. So this shows a commonly requested specification, so some of the more common gases that are asked for, and the priority that's given to them by customers, and the technology fit from the different technologies that we offer. So here a green yes shows that we have a good solution available, red no means that there isn't a solution for that technology for this application, and yellow, it's application dependent. So what you can see from this is there's not one technology that has green ticks down all of the different components that are needed. So in some cases, we're having to mix and match technology types to create an analytical solution for a particular set of measurements. So next, to talk about some case studies. So the first one is an enhanced oil recovery case study. So in this application, it was a US-based company using CO2 to enhance methane production from a well. So they were injecting CO2 into the well and wanted to measure it both at the injection well and at the production well. And that was to monitor the efficiency of the process. So in this case, we provided 2 Emerson CT4400 QCL analyzers to monitor CO2 at both the injection and recovery wells. So here they wanted a wide measurement range, so a 0 to 100% range with a low detection limit, a 0.25% detection limit. And I've put some of the data that we got from our factory acceptance testing, so showing very good linearity of response over the 0 to 100% range and a clear step to 0 at 0.25%. So these analyzers were selected because they offered continuous monitoring, had very fast response times, and a wide dynamic range for CO2 monitoring. So the next one is a CO2 transportation application where a US-based company was running a gas processing operation producing CO2 that was being transported from the site for use in another process. And before transportation, they wanted to measure any impurities in the CO2 to ensure the quality of it and reduce the risk of any damage to transportation equipment. So in this case, an Emerson 700XA GC was selected to monitor the bulk CO2 along with the inert components, and this had a dual TCD detector and was providing a measurement every 3 minutes. And finally, a blue hydrogen production case study. So blue hydrogen is created when the CO2 emissions from the production process are captured and sequestered to make the production process carbon neutral. And in this case, a European company was using a cryogenic method to decarbonize their site and capturing more than 100,000 tons of CO2 each year. And they wanted to monitor the composition of the flue gas from the steam methane reforming process to optimize the efficiency. So here the solution was 3 Emerson XEGP PGA analyzers configured to continuously monitor CO2, methane, hydrogen, and oxygen using a range of different technologies. And they were selected in this case due to their versatile measurement capability, multi-component analyzer solution, and that they're a cost-effective analyzer. So to conclude, so CCUS is a very rapidly growing market as companies strive to reduce their carbon footprint. Each carbon capture application and installation has different measurement requirements. And so we're proposing different analytical technologies which offer different strengths and measurement capabilities. So GCs can offer very complex gas stream analysis, Laser analyzers have very fast update rates and low detection limits, and process gas analyzers, which have very versatile measurements with a range of different technologies. And we need to keep a flexible approach when specifying an analytical solution for CCUS applications. It's not a one-size-fits-all type solution. Thank you very much.
Do we have any questions for Ruth?
Hello there. We did these systems back in '96 for offshore injections, and I noticed you don't have nothing about amines and traces of amines.
Sorry, measuring trace amines?
Yes.
So that's not come up in the applications that we've looked at so far.
Okay.
I like the laser technology for the quick updates. Could you tell me how many components I can measure with a single laser analyzer? Like ideally, I'd want to measure 3, 4 components in a single laser. Do we have that capability?
So how many components we can measure in a single analyzer? In a laser analyzer, yeah. So we can put up to 6 different lasers in a single instrument. So we can measure typically between 6 and 10 different components. So it depends. Sometimes you get lucky with the spectroscopy and you can measure multiple components on one laser. So 6 to 10 is typical.
Any other questions? All right.
Thank you.
Next up, we have David Sanz with Apex Analytics. David has his master's degree in analytical chemistry. He spent a couple of years with Total Energies in Pau, France, where he did development work in GC. And for the last 3 years, he's been at Apex in Grenoble, France, as an application engineer for them. In his spare time, he enjoys music and mountaineering.
Good morning, everyone. Thank you for the introduction. Today, I'm excited to talk to you about how silicon technology is reshaping GC and how we implemented that in GreenPeaks as a product and how it answers the market needs today. So before I start, I just want to start with a quick introduction about process GCs because some of you might not be familiar with that. So when do you need process GCs? The obvious answer is when you have a complex mixture and you need to know the exact content of your mixture, which molecules and at which concentrations. It is very important in the energy market because you might need to know the calorific value of your gas in order to sell your gas. You might need to know which impurities are present to transport the gas. And in the end, it's really about standard compliance. So there are tons of standards. Here I've listed some of them, but the point is that there are so many applications where, so many standard-driven applications where GC is either mandatory or inherently required because sometimes it's the only technique that can achieve the required accuracy in quantification and resolution. So some molecules also are very hard to do without GC. And when you compare other techniques with GC, you might have problems with interferences, like sometimes in spectroscopy, or let's take the case of in FTIR, for example. You have compounds that do not or barely absorb in infrared at all, like nitrogen. Let's take electrochemical sensors, for example. They may have a lot of drift over time, and this is less the case for GC. So really, sometimes you don't really have a choice, and you need GC in order to answer the metrological needs of some applications. And it's present at every point of the energy chain, from production to transport and distribution. So GC is a well-established technology, and yet it still needs some level of innovation in order to answer the newer market needs today. And I'm going to talk to you about how miniaturization is a way to answer those needs. In other words, why do we need to use micro GC? In the past decade, we've seen a rise in decentralized energy systems, like biomethane units, electrolyzers, all of which require compact, fast, and reliable analyzers. In smart gas grids, you need almost real-time data in order to optimize gas transport, and you can imagine why low cycle times are necessary in those cases. Let's take biomethane injection, for instance. When you want to inject biomethane, you need to monitor continuously calorific value, oxygen, hydrogen sulfide, and more continuously at the injection point, and with high sensitivity too, in the case of hydrogen sulfide. Hydrogen is another example. You might know about the ISO 14687 norm, which is a huge list of compounds that we need to analyze for hydrogen fuel quality. And it's the same deal. We need the trace analysis of all of those compounds that are listed here, for which micro GC provides a high-performance solution close to the sampling point. There's also the question of carrier gas usage, especially relevant with the price of helium today. And today, integration is a big deal for GC and for other analyzers, because often you have to integrate GC as part of OEM or into industrial skids, and micro GC makes perfect sense to use in those cases. So miniaturization is key, and it doesn't come with lower performance. It's a bit counterintuitive, but if you take smaller detectors, smaller columns, you work with lower diameters, you work with lower volumes, and ultimately that means less dispersion. And in terms of chromatography, you get higher chromatographic efficiency. So in the end, you get narrower peaks, taller peaks, and it's a rise in sensitivity, in selectivity, in resolution, sorry. And you can also afford to push faster, so it's a speed gain as well. So micro GC provides a path forward where traditional GC may fall short in terms of compactness, in terms of response time, in terms of deployment flexibility. And here you have the three core components of a traditional GC, traditionally in stainless steel, of course. And I'm going to be showing how one way to miniaturize each of those elements, from the injector to the column that we'll see at the very end, and to the detector. But first, let's talk about the material choice that enables us to perform such miniaturization: silicon. Silicon isn't just motor. Using microfabrication, you're able to fabricate microvalves and fluidic channels with extreme precision and reproducibility. There's a big potential for mass production. It's very much like in the semiconductor industry, where once you have your process, you're able to manufacture thousands of units very consistently. Another key advantage is the thermal performance of silicon. Silicon is very easy to heat and to cool down, and it allows us to do rapid temperature ramps, rapid regenerations, and overall lower cycle times, and of course, lower power consumption. I already talked about microfluidics and how it enables us to increase chromatographic performance and reduce carrier gas usage. So really, silicon enables us to shrink GCs down to a level that just isn't accessible, isn't feasible with traditional GC hardware and tubings. Well, it is a size revolution for GC, and it isn't much unlike how we turned computers from the 90s into smartphones that we have today. So let's see how we implemented silicon miniaturization in GreenPix. Let's start with the injector. Injection is extremely important in GC because you need to deliver a repeatable and precise amount of sample into your column. In GreenPix, we have a fully microfabricated silicon injector that's mounted on top of a glass splitter and a manifold that's free of any tubing. It's all internal tubing, and this is a fully tubing-free design. Here, injection volume is defined by time. It's very important because you are able to precisely manage sample volume using software time instead of needing a hardware change that's usually required with traditional valves that use fixed sample loops. So you're able to both inject a low amount of sample for percentage level analysis and a large amount of sample to optimize trace analysis. Of course, it's very repeatable, and here you have an example for THT, which is a common odorant. This is the injector linearity curve measured on THT. So peak area as a function of injection time. And you can see that, of course, well, it's linear down to a certain level, which is the response time kind of the instrument, and the up to the full loop injection. It's a very versatile way to inject in GC, and it's very useful in many cases. Now let's talk about detectors. So in micro GC, we mostly use micro TCD. I'm not going to expand into the physics of micro TCD because, well, it's thermal conductivity, and we've seen that in a previous presentation. I'm going to focus on the NGD detector, which is the other key technology, which is proprietary to Apix Analytics. And well, I'm not going to expand very far into the physics. Could be a whole presentation. You've got a paper reference here at the bottom, and we can chat anytime that you want. All I'm going to say is that it is like a mass-sensitive detector that measures shift in frequency of a resonating beam after compounds may or may not absorb onto the resonator after exciting the column. So naturally, it is sensitive to mass, and it is very sensitive to mid to heavier hydrocarbons, where TCD may fall short in terms of sensitivity. So of course, it complements micro TCD very well, and sensitivity can even be tuned by temperature. So really, the point of using the NGD is also as a replacement for the FID on the field, where we have a naturally 8x compatible design because of silicon, because there's no flame, and because, well, we are not sensitive to carrier gas, so we are able to use it with generated air or hydrogen, whatever. You will see chromatograms of the NGD later with applications. So, once you take all of that together, it comes to life as GreenPix. This is the name of the product. So, GreenPix is a modular GC architecture, and each module is a self-contained GC with its own electronics, its silicon injector on the left here, its silicon detectors on the right, either TCD or NGD. And this is not a silicon column. We will see what a silicon column is, but here it's still a capillary column. So all of those elements come together as the module that you see here. And really, all of those elements are what we need to put together in order to assemble the GC. And for an operator, it's less than 15 minutes assembly time. The assembly process is really streamlined because we can pre-assemble all those parts using pick-and-place technology thanks to silicon. And you can really see how it's designed for OEM thanks to the size and thanks to silicon technology because, well, if you need, well, this is a module here. If you need a single column module for a simple application, well, you can easily integrate this module here in whatever process you're doing. If you need an autonomous GC, well, I have one here. You can just put it in an enclosure here. It's about the size of, this is the module that's inside of it. And there's just a small enclosure with a computer running the software. If you need to do something more complex, well, you can chain the modules together. You can chain the modules like you see here. The manifolds can be chained without tubings, so it's still a tubing-free design, and it's scalable. It's scalable. So you either put that into your own box, or here it's a picture of an IAPIC system, but the point is that integration is very, very easy. Now, let's talk about real use cases and real applications. Let's start with hydrogen sulfide, H2S. H2S can be tricky because of low detection limits required by regulations. And in Europe, for instance, I think it's about 3 ppm or something in the pipes for biomethane. And often, companies like to buy sulfur-specific detectors in order to have more margin, you know. Well, what this shows here is that this type of application is easily accessible to micro TCD, for which we obtain limits of detection close to a little bit less than 1 ppm. So what you see here is 4 ppm chromatogram and repeatability over 14 hours, about 2%. This is a prime example of an application, a single module application that can be easily embedded into any system and can fit in the box that I just showed you like this. Now, trace oxygen and nitrogen is a crucial application in a crucial problem in hydrogen purity and carbon capture. I mentioned the ISO 14687 norm. Well, as far as I know, GC is one of the only way to measure nitrogen at such concentrations for this norm. And oftentimes you need to integrate the GC with other instruments because of the sheer amount of molecules that you need to analyze, and GC can do them all. So the compactness of the product is very, very important in this case. And here you can see the analysis of oxygen and nitrogen at 10 ppm levels, with limits of detection with micro TCD obtained at approximately 1 ppm. For those of you who are familiar with this type of applications, you know that the tubing is very important, and if you don't have clean tubing, you have air intakes from everywhere, and you do not obtain clean blanks. So it is not shown on this picture, but of course, we were in a scenario where we obtained clean blanks. This is an emulsive column, by the way. And this is another example with emulsive column for permanent gas analysis, this time in biomethane plus H2. So emulsives are tricky because they're very good at fast analysis of permanent gases, but they are very hard to use in a stable way. They contaminate over time, there is a lot of drift. And here, the point is that retention times are very stable, so it's not showing long-term stability here, but we are using micro-GC technology, which, as I said, allows you to heat your columns very fast. And it allows you to regenerate your column every now and then, every couple analysis, without any compromise in cycle time. So it's a way, micro-GC is a nice way to use emulsive columns in a very stable way. And it's basically stable with no user interaction at all. So this is an important point because it's crucial in many applications, oxygen in biomethane and what you saw just previously, impurities in hydrogen or carbon capture. I mentioned fast analysis. Well, one way to go even faster is to use hydrogen as a carrier gas. And you have an example here with hydrocarbons up to C5. Well, hydrogen with TCD is not meant for everything, of course. But here, it's a good application because we lose just a little bit of sensitivity with a 20–30% gain in cycle time. And this result here shows that we obtain this separation in less than 25 seconds with very high repeatabilities. You might wonder when we need such low analysis times, and one prime example is mud logging. Because in mud logging, you have people who are mapping the underground, well, the cycle time is basically defines the resolution of the picture they have of the underground. So even a small amount of gain is a big gain for this application. Of course, micro GC is also very good for more traditional application. And here you have an example with C6 plus analysis for calorific value measurement, BTU, especially for custody transfer. And what this shows here is a separation in less than 100 seconds with baseline separation of between C4 and Neo C5, which is made possible because of the injector technology and the sharpness of the peak. So very good repeatabilities here as well. We are undergoing the process of going to more in-depth testing in order to certify this equipment for this application, which is governed by many norms. One word about the NGD, last application, one word about the NGD. I mentioned its sensitivity to heavier molecules, C6 to C12 and beyond. Well, on the left here, you have an example, mix C6 to C11, and you can see the limits of detection start to get down to ppb levels after C8, which is not accessible for TCD. An obvious application for this case is accurate dew point measurement. So these are the limits of detections obtained in these conditions, of course. I mentioned the fact that the sensitivity of the NGD can be tuned by temperature. And this is what you see on the right, with another example using THT, the same odorant as previously. What you see on the chromatogram on the bottom right is how a peak area increases as you cool down the NGD. And the curve on the top is area as a function of the NGD temperature, shows you that it's an exponential gain. So it can be very, very sensitive in cryogenic conditions, and it's especially useful to target specific molecules like siloxanes, and in this example here, THT is an application for deodorization, like the removal of THT. So it's a very versatile detector. Just one word before I finish about silicon columns. Well, this is still in development for the company, but this is also the future for us. So silicon columns are structures, geometries that are built on top of silicon wafers in order to have the same behavior close to packed columns. And once you start putting coating on these structures, you have a level of separation. And here you can see some of the early chromatograms that we obtained for, well, I probably can't read anything because I can't either, but this is VOCs and hydrocarbons separated in less than 10 seconds. So of course with a high pressure. And the speed isn't the highlight of that. The highlight is that it's the last step necessary for complete miniaturization, because once you take together a silicon injector, a silicon column, and a silicon detector, you are ready to have a true GC on chip. And this is what is shown on the left here. This concept here on the full silicon GC which is smaller than a smartphone. So this is good perspective for us, and we are excited about the future of this. Well, thank you for listening. I'd like to thank the European Innovation Council for financing the studies related to GreenPix. One word about APIX. We are a small company in France, based in Grenoble, with offices in Beijing in China. We have over 1,000 GCs installed worldwide. And in the US, we work with Elemental Enterprises, our distributor, who are a team of hardworking people and skilled people, just 1 hour away from Houston. So we have a booth together with Elemental at 624, 626. So if you're around, don't hesitate to come by and have a chat. Thank you, and are there any questions?
Thanks for the great talk. I'm trying to understand, so you did a very good job of showing the capabilities of silicon, but I'm trying to understand its limitations. Perhaps you could shed light on that, perhaps cost. I'm also looking at the nanogravimetric detector. Mm-hmm. You mentioned sensitivity increases with decreasing temperature.
Yes.
Doesn't that limit your applications to non-condensable gases?
Does it have applications to what, you said?
Because if you lower the temperature enough to increase your sensitivity, you might have some gases that would condense out.
Yes, of course. Well, so, I went very briefly on the NGD. As I said, it could be a whole presentation, but on the NGD, we like to do a temperature ramp because the principles of detection on the NGD is adsorption. So you're right in saying that molecules could just never leave the detector. They could adsorb forever. So what we do in these cases is we do a temperature ramp on the NGD. So this allows them to leave the detector.
Okay. Well, anyway, I just, perhaps you could share the limitations, the drawbacks of silicon.
Yeah. Well, one of the drawbacks is very, very heavy molecules. Well, silicon has a temperature limit when heated. So it's about 250 Celsius. Obviously, any molecule that cannot desorb past 250 Celsius is stuck on the detector. So one limitation is that you cannot analyze very, very heavy molecules. The detector itself has a coating, so a chemical coating, and it acts kind of like a column, So as long as you are able to have the compound exit the column at this temperature, you know that it will dissolve from the detector. But if not, then you're stuck. And you can actually have a case where you reduce the number of sites, active sites in the detector, and you lose sensitivity this way. So you're right in saying that it's a limitation of the detector. You have to work in a precise temperature range which is allowed by the temperatures that you can program on the silicon chip.
So I have a question. Do you have special requirement on the sample conditioning system for using this macro GC? Because my concern is if there's a process upset, there's liquid or sticky stuff get into your GC. How do you clean it up?
So once the compound enters the column system, no problem. It's all about before the column, the injector and the sampling that comes before the GC. So we use a lot of aluminum and we use glass. And the thing with glass is that it's not that sticky at all. And we are able to have treatment on the tubings inside of the analyzers for the cases where we analyze things like sulfurs, sticky stuff like sulfurs. But we have the same challenge as any other GC when it comes to stuff like ammonia that sticks everywhere. It's the same stuff. So any kind of treatment that is able to be applied on tubings in general, we have the ability to apply them in GreenPix as well. But the hardest part is getting the sample into the column, So right now, in our product, we have no problem with the levels of sulfurs that we're analyzing, which is our main business. But of course, I expect that if we tried ammonia, we will need to work a little bit more on the treatment of the analyzer, ammonia and other stuff, of course. But you're right in saying that it needs some treatment in order to sample any kind of gases.
I'm interested the absorbance. Is that the pure?
In what?
The absorbance on the NGD
yes.
sensor is that pure solid surface, or you have absorbent deposit on the surface? If you have that, and does that how long it can survive?
How long it can survive? Well, if you send some nasty stuff, yes. Yes, the coating, I understand. Well, the type of coating, I cannot share the very specifics, of course, but as I said, it's like a column. So anything that can destroy a column can destroy the NGD. But we can change the coating of the NGD. And we can have several detectors in order to target specific molecules. But if we don't use, let's say, a guard column system to prevent the nasty stuff that would destroy a column in the same way that it would destroy NGD from coming inside of the column, yes, we expect that the chemical layer of the NGD could be destroyed that way. So we have to protect it, and we can do it chromatographically using guard columns and so on. So yes, it's really about what type of chemical layer is on the NGD, and the basic one is it's like a column, and it's not destroyed by a lot of stuff. But if you put like a hydrofluoric acid, like I mean, even silicon itself will not withstand it, you know. So you have to be careful about the chromatographic columns that you use, so that the nasty stuff doesn't get into the detector. Yes.
Hi, great presentation. I just have a question as far as like methods for C6+. When you're sitting around 20 to 30%, have you tried any applications such as that?
20-30% of speed for fast hydrocarbon analysis. Is that what you're asking?
Were the concentrations of C6+, like a higher concentration of like Connie analysis?
Okay.
Like 60, yeah.
Well, the application that I showed is a baseline of C6+ applications, and in the cases where you have higher concentrations, like LNG, for example, where you may have a huge amount of propane or butanes, you might need to review the method a little bit and inject, and in fact it's one of the strengths of the injector. You are able to inject a lot less sample thanks to the micro-injector technology, so that your peaks do not overload in the column, because when you're working with micro GC, you often have low diameters in the columns, and it's very easy to overload, and then you lose linearity. So the micro TCD detector itself, it's linear, okay? It's linear between, let's say, 0 and 100% with very small variations. Now, any type of non-linearity that you might come across come from column effects. So you need to be careful not to inject too much sample. And for your question, 20-30% of sample is no problem. And more than that can be achieved even once you start to play with the injector and inject less and less sample. So it really depends on what you're expecting. In a classic application, what I showed works perfectly, but you might want to inject a little less sample for complex applications where you expect a lot of sample. Does that answer your question?
Yeah, a little bit, but I was more kind of gearing around with the high concentration of the C6+ in the sample. Would it be harder on the analyzer? Like, would it gum up? And
okay. So you're asking about specifically C6+ as a compound, right? Well, as a mix of compounds.
Correct, yeah.
Well, the thing with high concentration C6+ is that it's a mix of many things. It could be a mix of many things. It could be a mix of C6, C7, C8, and we are quantifying a single peak. So Any kind of inaccuracy with that comes from the fact that you don't know what the mix is made of. So with high concentrations, you have this possibility that you are inaccurate from the fact that you do not know the coefficient of quantification is usually like an average coefficient. But in these cases, you may use an NGD detector or others in order to have, instead of quantifying C6 plus as a single peak, you may have the detail C6, C7, C8, and therefore have a more accurate representation of your sample. It really depends on the application, but for custody transfer at least, and what's associated with the usual concentration limits, it's fine, really, it's fine. And even if it's just an approximation, if you need something more accurate, you need to know the detail of C6 plus, of course.
Okay, great. Thank you very much.
No problem.
We've got time for one last question before we go to lunch.
Yes, what size columns do you use, and are the modules repairable on site?
The question is, can you repeat the question? I don't hear very well from here, sorry.
What size capillaries do you use?
Oh, it's micro or nanobore. So it's usually 0.25 millimeters internal diameters or less than that.
1/8 inch? 16 inch?
An inch, I have no idea. But
second question is, are the modules repairable on site?
On site, well, the advantage of having the modular architecture is that you just swap modules. Like you just remove the old one and put the new one. If you want to repair a module on site, well, you are faced usually with operators who might not even know GC, and the major concern about repairing a GC is usually repairing the column. So, of course, they can do it because of how simple it is. Because if I go back to the slide that shows the module itself here, it's like 4 screws, then 4 more screws, and you have access to the column. So as long as they have expertise in changing columns, it's easily accessible. But usually we never do that on site because people don't like to change columns. They like to break it. So usually they buy multiple copies of the same module, and if something bad happens, they can just swap for a new module, you know, and maybe repair it in more favorable conditions, like in a factory or whatever. But usually on site, with all the dust, everything, it's a difficult operation to change a column on site. Something that's very easy to change is the electronics that you see on the top here. If there's any problem for any reason with the electronics, it's very easy. But column is a different topic.
All right, that sounds great. So that concludes session 3. There will be lunch in the Vinner Hall, and so after lunch we'll have talks back here at 1 o'clock. Thanks.